All right, so let's talk about chapter 3 for homework 2. And just looking at the book here, what first comes here in chapter 3, they have a little introduction about some person here. And, optional if you want to check it out. It's really talking about teaching physics in an intuitive way, which there are absolutely teachers who have that position. I don't. uh, physics wouldn't work without math. Math is what describes physics. If physics was so intuitive, then why isn't everybody an amazing physicist? So that's my position. If you want to check out the more intuitive approach, this is what the book is doing. When you read the book, it's trying to explain things happening in a non kind of mathematical way. And, there are people that support that. I'm more convinced that we got to tell what the truth is. Math is heavily involved in physics. And the state of things today actually is math mostly drives physics. That when you search through your theories, and this is me kind of searching through your theories, and math makes predictions, and then you test it and you find it's true, and you're like, wow, math is pretty amazing. So just a little perspective there. They do have an intuitive approach, and I'm just going to show you the hopefully simple, straightforward math way to solve this stuff. So checking out to the next one, speed. And speed is best defined, I would say, right here with average speed. So, if you have some distance, maybe you start here and you travel to some point here. Well, you traveled some distance. And that's what they mean here first by this total distance covered. It's the distance you traveled to go from one point to another, from A to B, however it is. That's our total distance that we traveled. And we did that in some time interval. So, maybe you had a stopwatch and you went from A to B using your stopwatch, and you get some time value from your stopwatch. And, you measure the distance, whether, I was going to say with a ruler or something, but hopefully you have something bigger for a longer distance. And then when you take these two things, distance divided by time, that's how we define an average speed. So this is an average, and we're going to talk about the difference between the average and not the average. And that's our first math that you're going to want to have down here that solves these things. How do we define things? We define average speed then as the distance you traveled, and then divide that by the time it took to travel that distance. And then we define that as average speed. And they give some examples here, looking back at the text. But I want to scroll up a little bit to this speedometer here, because they mention this word instantaneous speed. And normally, when you're getting hardcore about stuff in physics or engineering, you want to know what's happening right now. At this moment in time, what is my speed? If I travel 10 seconds, what is my speed at 10 seconds? And this is what we call the instantaneous speed. And overall, this is what we tend to prefer in physics because, we want to know at, 5 seconds, what is your speed? And that's the picture of the odometer here, what I think they're trying to give to you, that when you're driving your car and you look at the speedometer, that is your instantaneous speed. So at every moment in time, the speedometer is giving your instantaneous, the speed you have at that moment in time, where the average speed always covers some time interval. So over this interval is average speed. But let's say at some moment in time, like maybe right here, I wanted to know, what's my speed right here? I forgot a D there. What's my speed right here as I'm traveling along? Well, that's our instantaneous. So we have this average speed, which is, can be useful sometimes. Normally, we want to know the exact speed at some moment in time. And what makes things a little bit tricky with 101 is the exact speed is obtained with calculus. And of course, we're not going to get into any of that. And so we will do two equations that come from calculus. They'll be simple and straightforward. The book presents them as well, so I'm, just want to make sure you understand. I'm not going beyond what's the book, even though I take a more mathematical perspective towards physics. So instantaneous, that's calculus stuff. That's normally what we want, but we will be dealing more with average speed over some distance, over some time interval. And just scrolling through, they have this other equation here written with words. So it's up to you. I don't like writing the words out, so I'm just going to use, D and T for my, usually we'll say speed, like maybe as an average here. And all they're doing with this word statement is they're just multiplying both sides by T. If you multiply both sides by T, then these cancel, and you're left with then your total distance traveled is your average speed times time. And then that's what they're saying here. This total distance covered equals, so total distance covered equals average speed times your time interval. And it's really just the same equations. These are the same equations. They're just written differently. It's the same relationship. And this last part here, motion is relative. They have a happy sun, I guess with some green object, definitely not Earth, going around. And they're trying to say to you, let me say this. I think an easier way to approach relative speed while not having a happy sun there is imagine you're just standing on the ground. You're just standing on the ground and you're looking out into the distance. And into the distance, you see a train. Now, I'm going to draw very simply, that's my train. And you're looking at it. And say the train is traveling 30 miles per hour. Well, you look at it and you take your measurement. You're like, yeah, it's traveling 30 miles per hour. But what if another person is walking on the train and they're maybe walking at 2 miles per hour on the train? Well, from this person's perspective, when you're on the train's ground is stopped to you. So when you walk, you're walking 2 miles per hour with respect to the train. But outside, this person is seeing you travel 30 miles per hour plus the 2 miles per hour you're walking. And so, this person's going to say, hey, your speed is actually 32 miles per hour. And this is what relative in the book here to the right, what they're saying, motion is relative, that this person sees this person's motion as 32 miles per hour, while this person would say, I'm traveling 2 miles per hour with respect to this train. And that's relative speed. Now, if the person was walking backwards, let's say we forget this part, instead the person walked backwards at 2 miles per hour, well, then this person's going to say 30 minus 2 is then going to be 28. Because the train's going 30 to the right, the person is going 2 to the left now. So the left is going to meet a minus sign here. So we're doing 30 minus 2. And so the relative speed, the person on the ground is going to then see that as 28 miles per hour. And with the sun, just going back to the book and the sun, I think what they're saying here is when you stand on the earth feels like it's at rest. And so when you walk around on the earth, we measure our speed relative to the Earth. Think about right now. You're probably sitting down right now, and you probably feel like you're not moving. You're sitting there watching and listening to this. You're not moving. But in reality, the Earth is moving around the sun. So from our perspective on the Earth, it feels like we're not moving. I'm just sitting in my chair. But if somebody somehow was looking at our solar system, kind of looking, well, if this is our sun and here's our planet going around, if we had a big eyeball looking down at us, then they would see us moving. They'd be like, oh, you think you're standing still on the Earth because you're just sitting there. But from my view, I actually see you speeding around this sun. They see another velocity. And if we had an even bigger eyeball and looked at, say, now I'm kind of draw galaxies here, but our sun, about right here. So not only do we spin around the sun on Earth, but the sun also spins in our galaxy. And so in an even bigger eyeball looking at things, they'd be like, well, you're spinning around the sun and the sun is spinning around these galaxies. And I guess just to finish that idea is that even in bigger eyeball, even a bigger one, and I'm trying to draw galaxies here in a very rough way. Maybe here's ours with the sun. Here we are orbiting it on Earth. If we had an even bigger eyeball looking at things, and here's us on Earth, they would say, I see you spinning around the sun. I see the sun spinning around in your galaxy, and I see your galaxy spinning around with these other ones. And relative motion, to get even more technical, Einstein, he came up with what's called the general relativity theory, and he's arguing that there's nothing in the universe that isn't moving. Everything is moving, and we're orbiting around all of this stuff. Now, you don't need to know anything about universes or anything there, well beyond kind of what the text is going there. But just to give you an idea of relative velocity, I think the best one is looking at the train example. I think that's nice and straightforward. I think the sun's getting a little carried away, but I had a little fun with it, trying to go into galaxies and stuff in the bigger picture there, but you won't need that for the homework. Just the idea of the train car and subtracting or adding numbers is what the homework will have. And that is speed. So going to the next one, velocity. And there are different objects in math. And you're probably familiar with coordinate systems. A number really represents just some quantity. In math, it usually kind of represents the distance from the origin, but it just represents a quantity. A number has one piece of information, one, and that's it. And the only piece is that number, the quantity. The next in line, so one piece of information. The next in line, it has two pieces of information, is what we call then a vector. So this is a number, one piece of information. The next in line comes a vector. And a vector contains a number and a direction. And the direction is also a number. But it contains these two pieces of information. It contains a length we commonly draw with an arrow. So this has some length here. That's one piece of information. And then if I put it on a coordinate system, its angle is the other piece of information. So a vector, two pieces of information. And we define these things. Now I'm going to get a little overboard, meaning this is beyond the homework, but just to give you an idea, we would write in the x direction, and it's called I hat. It's a little, because it looks like a little hat on it, but that's the math symbology there. And it just it means to the right. So if I say to I hat, that just means go to the right twice. If I would write minus 2i hat, that well means go to the left because of the minus sign. And if we use words and we say, if we would say, drive 10 miles east. Well, you know, those are good words, but in physics, you want to get things into math. And so to the east, mathematically, this is our little I hat. And so 10 miles east, those words, we then write in math as 10 I hat, where the I indicates the direction. And just to go back, a number, one piece of information. The vector contains two. The two pieces are the number, the miles you're traveling, and then the direction. East, in math, we define as this I hat. Where if I said, say, 5 miles west, well, then that would be minus 5 hat, because we're going minus to the left, west being to the left, and going 5. And we're not going to deal with the vector part, so this I hat, don't freak out. We're not going to be dealing with any of that in our book. It's, like I said, it's a little bit beyond. I'm just trying to give you the idea that a number contains one piece of information, a vector contains two. We're not going to get hardcore math with the vector, not at all. But it is important to know it contains two pieces of information. It contains the distance we're going and the direction we're going in. Those are the two pieces. And that's what they're talking about. So we ultimately call this velocity. So speed, we had that average speed. That was our distance traveled over our time. And now velocity is technically defined with calculus. I'm just going to scroll through here really fast in our book just to see what they say. They don't say anything for the math of velocity. So let me just say this. I can't give you an equals. Well, I don't want to give you an equal sign here because then I'd have to write a piece of calculus next. But I just want to say velocity is defined. There is an equal sign, and what comes next is calculus stuff. But our book isn't doing that. Just trying to give you what the truth is here. And so our book is only going to deal with speed and direction. So you can see we have no definition for velocity, and so we're not going to have to worry about that. Our velocity is going to be for us. If I say, well, let me scratch that. If I say 10 miles per hour, this if you're wondering, you know, what do I need to know here? This is what I'm going to tell you right here. If somebody says 10 miles per hour, that's a speed because it only contains one number, one piece of information. It's a number. It's not a vector. Now, if I would say 10 miles east, or if I go, 10 miles per hour east, well, this is now a vector. And the vector is what we call then velocity. So if somebody only gives you your speed, well, then we call that speed. But if somebody gives you speed and a direction, we call that velocity. And that's really the difference. That's what you're supposed to take away here in 101. Because, you know, there's no calculus. We're not going to get in that hardcore math. What they want you to know here is that if I say 50 miles per hour north, that you understand there's a speed, there's a direction. Physics calls that a velocity. And if you tell me 30 miles per hour, well, that's only a speed. And that's the difference you're supposed to take away here. The difference between speed and velocity. One is just the speed. Velocity is speed and direction. So checking out 3.3, and they're going to give us a definition for acceleration. I'm just going back to 3.2. They didn't give us any math for velocity, all right? But they are going to for acceleration. Let me say this. The delta in math, always, no exceptions, always defined as final minus initial. This triangle symbol in math, it's called delta, and it's literally defined as final minus initial. We can, in algebra, take velocity and kind of loosely, lazily, not exact, define this as delta x over delta t. And we'd have to give some direction. And the reason I'm just throwing this out there is because now they're talking about acceleration, and acceleration is change in velocity over change in time. And so they're giving us acceleration. They skipped the velocity one though. I think maybe that's a mistake, because maybe this is a little bit more out of nowhere then. So what we start is, and here's how we do it, is we have some position. You travel some distance. We call that delta x. If you travel some distance. It's a way we can represent it mathematically. And just to be, that's an equal sign, just to be as clear as possible, if you travel here and you go to here, well, this is your initial position, this is your final position, and then final minus initial is this distance. And so this is our distance traveled. And then the next thing we do in physics is we divide that by the change in time. And that's how we get to velocity. We take our distance traveled, we divide it by time, we get velocity. Now, I know this looks a lot like speed, and it is. We would have to include some direction on here still. Since we're not getting hardcore into the math, we should probably have a word here like maybe east or north. And then what happens is after we have velocity, so velocity is how our distance changes with time, but you all know your velocity changes. So when you're at a stoplight, you push on your gas pedal, the accelerator, you know your car increases in speed because you can feel it, you can see it in your speedometer. And so you're experiencing a change in your velocity. And that velocity can change over time. You experience that when you're at a stoplight. You start with a velocity of 0, and then you work your way up to the speed limit. That's your change in your velocity. And then your change in time. How long did it take you to do that? And then we call that acceleration. And that's what they're defining here. Acceleration is how your speed changes. And it's the pedal in your car. The pedal in your car is literally called the accelerator because it gives you acceleration. It changes your speed. So to say that again, we can represent distance like this. And then our next value that we're interested in is, well, what if we took this and divided by time? And then we get velocity. And then what if we would take the velocity and divide by time? Well, now we get acceleration. And again, acceleration is how your speed changes. And looks like they're giving some examples here, just some numbers. We'll check that out when I do some of the homework problems. Okay. So the book is going to go here. So I'm looking at this red box here. So going back to a velocity, we define acceleration. We define acceleration with how velocity changes. So there's two cases in how that can happen, because a velocity contains two pieces of information. So the velocity contains, here's my velocity. Very common to draw with an arrow, because an arrow has a length and a direction. And those are the two pieces of information for a vector. Now this velocity, maybe the arrow gets shorter, but the direction doesn't change. Well, if it gets shorter, that's a change in velocity, which means there must have been an acceleration. And this is what you experience when you're driving on a straight road. And straight is important here. That when you start at a stoplight and you're on a straight road, what you're changing is the length of the velocity vector, but you're not changing the direction because you're driving on a straight road. So when you accelerate your car, whoops, I did not want to draw an arrow there. When you accelerate your car, your velocity vector starts out very small. And then as you accelerate, it gets larger. And then as you accelerate, it gets larger, your velocity. But it's always at the same angle because you're driving straight. This is one way of getting acceleration, by changing the velocity, changing the speed. The other way is when you're not driving straight. So for instance, driving around a corner. Now when you drive around a corner, and I'm sure you've all done this, imagine you're driving around a corner and you're maintaining the same speed. So let's say the speed limit is 40 miles per hour. You drive the corner, you're driving the corner at 40 miles per hour. So it seems like, well, my velocity is not changing because my speed is constant. But velocity needs also a direction. And when you turn, the vector, the velocity arrow, changes direction. So when you go around a corner, your initial velocity vector is going straight up. Remember, you're driving 40 miles per hour, so this length doesn't change of the velocity vector. But as you turn the corner, its direction changes. And that direction change also requires an acceleration. And this is the part that, one of the parts about physics can be a little confusing. And that has to do because the velocity is a vector. It contains a number, a magnitude we call this, and a direction. It always contains two pieces of information. And because there's two pieces, means there's two accelerations then that can change this. We can either change the speed or we can change the direction. If either of those change, or both, then we have an acceleration. So, if you are increasing your speed going around this corner, well, the vectors will still turn, But if you're increasing your speed, well, then they'll be longer, but they'll still be turning. And that's what they're trying to say in the book over here, looking at the red box. They're trying to say there's 3 controls. I get what they're saying. Okay, the accelerator, increases your speed. The brake reduces your speed. And then the steering wheel changes direction. And that does all change your acceleration. Brakes, I'll take brakes. My brain, it's just being a little bit more specific with the math. But when you hit your accelerator pedal with your foot, I'm not even going to try to drive a foot. Well, here's your accelerator pedal. When you push that down, that does give your engine more gas, causes your acceleration to go positive. Braking, though, we would actually consider to be a negative acceleration, because when you brake, the acceleration then points against your car, but we still call that an acceleration. So the word brake here, I know what they're saying. Technically, the brake is causing some friction, and that friction is what causes the negative acceleration. But we do consider the brake to be acceleration. It's just negative of what your accelerator does. So your accelerator gives you a positive acceleration, while braking gives you a negative acceleration. And then turning your wheel gives you what we call a centripetal acceleration. And you don't have to worry about that word. I don't even think they mention it in our book at all. But that's what we call the acceleration that causes you to change directions. We call that centripetal. And this goes back to, I'm looking at the red box here, a point in the last video that zero acceleration doesn't mean you're stopped. So if you have zero acceleration just means that your velocity isn't changing. So the only way to get zero acceleration, so if you're traveling in time, which is delta t, if you're traveling in time, the only way to get A to be 0 is if there's no change in your velocity. Your velocity can't change. That's the only way to get acceleration 0, is that you have constant velocity. And there's many ways to get constant velocity. Maybe at 2 seconds, you're traveling 40 miles per hour, and then 5 seconds later, you're still traveling at 40 miles per hour. And so when you subtract those, you get 0 change in velocity. Now, it's also true, you could be standing still, and then maybe 10 hours later, still standing still, and that is still a 0 change in your velocity. And that's the point they're trying to make. And this is another part that can be a confusion and with the physics, is zero acceleration means no change in your velocity. But that doesn't mean you have no velocity. And that's what they're saying. Zero acceleration doesn't mean zero velocity. So zero acceleration we call constant motion, because your motion isn't changing. Whether you're driving at constant speed, we consider that constant motion, or if you're just sitting down where you're not moving, we also consider that constant motion. So I guess maybe that's what might be confusing there, because, the car's moving, and we consider moving to be motion, where if you just have a book on a table, people don't usually consider that to be motion, because it's not moving. And now just thinking about it, maybe motion seems to, people not learning physics, motion seems to imply movement. But the way we use constant motion in physics is constant motion literally means no acceleration. This is what we mean in physics by a constant motion. And then the math allows 2 scenarios to come from that. if the acceleration is 0, well, that could mean we're driving the speed limit or that our book is just sitting on a table. Both of these cases have 0 acceleration. And then we call that in physics constant motion. And I know there's a question in the homework about these ramps here. And this is what Galileo did. He did do a bunch of ramps, and he would have kind of a ruler etching on there so he could make his measurements. And they're just talking about if you have a ramp in these types of fashion, that once the ramp gets vertical, then it's just falling due to gravity. And that's what they're showing way to the right, where they say acceleration equals g. They're saying this object that's falling, when the ramp is vertical, and basically which means it's not touching the ramp anymore, then it's falling with the acceleration due to gravity. Where when there is contact with the ramp actually pushes back a little bit, and it has to, because if the ramp didn't push back, then the object will fall through it. If there was no force to hold this object up, then it would fall through the material. But it doesn't. It's on the ramp. And that's because there's a force that's supporting that. And that force does slow the object down so that you don't have the acceleration due to gravity. But once you get your ramp to be vertical, which means that now it's just falling straight down, the ramp isn't slowing it in any way. Now it's what we would call free fall. And free fall means when your acceleration is only gravity. Only gravity. And something that kind of annoys me, and I think our book has a question like this too, is they'll ask something like, when an object falls with air resistance. So if I have an object falling, and I'm kind of, mimicking air resistance here. If an object is falling with air resistance, is this free fall? And the answer is no. Because specifically free fall means nothing else but gravity. And sometimes I don't know, I see this kind of a trick question, but free fall is technically only the acceleration from gravity. There's no other forces, there's no friction, there's no air resistance, there's nothing. Free fall literally means the only force is gravity. And so the book, people try to trick you sometimes by throwing air resistance in there and stuff. But that's what free fall means. It means only gravity, nothing else. So, the next section is called free fall. And now G is technically 9.8, but our book is using this as 10. That's fine. 10 is a nice, easy number to use, especially versus 9.8. So they've got data tables. They kind of hope you fill in. A lot of reading. And again, if you want to read that, that's what the book is for, to get a different perspective, an intuitive perspective, because that is the book's approach towards things. But let me say this, and then I'll go through the book here a little bit more, is that this is where we have two equations that come from calculus. So Isaac Newton came up with calculus in trying to understand how motion worked. And through that math, he did a lot of stuff. But the two equations important to us that he gave us here was that if you have a final velocity acceleration, time, and an initial velocity, then this is how they relate to each other. And our book does use this one. Another one Newton gave us is that our distance traveled here is going to be 1/2 times the acceleration, time squared, plus initial velocity times time. These two equations are something that come from Isaac Newton, and our book presents these in a slightly simpler format. And what they do is they say the initial velocity is 0. And so that takes equation 1 then, and just to be velocity equals acceleration time time. And this is how our book presents it. And then the second one, since the book is saying the initial velocity is 0, means this part becomes 0. And so then the book presents just this part of Newton's equation. So these are the two our book presents. And these are simplified versions that come from Newton and calculus. These are actually Newton's equations here with velocity, with initial velocity 0, we get the equations that the book is presenting. And so, like this table, it's got time of fall and velocity acquired. So, for instance, they're asking us to fill in 6. They want to know what is the velocity at time equals 6. That's what they're looking for to fill in this row. Well, we just go to this one right here. Now, this is something that's falling, which means A is g, acceleration for gravity, which is 10. And then it's g times t, where t is 6. And so 10 times 6 is 60. And that would be our next entry. At 6 seconds, the velocity is 6. Well, what about if the velocity, what's the velocity when time is 100 seconds? So well beyond this table here. Well, we just use this equation again. If g is 10 meters per second squared, the acceleration due to gravity, and time is now 100 seconds, well, now we've got 1,000 for our velocity. So that's what the table is there. It's really just plugging in these numbers. It's about plugging numbers into this equation is what that table is. And here's where they present it. They have it right here, V equals GT. And so that's because that case was free fall. So remember, free fall is when the acceleration is only gravity. And so V equals GT for free fall. And that's where they're presenting that equation. And here's where they're trying to, develop an intuitive understanding of how things fall. It doesn't work for me. And again, maybe my brain is too much into the math end of things. But hey, I'm not saying not to read it. If that works for you, that's awesome. So they're just trying to explain how if you just drop something. So let me say this again. They're dropping something. And that means your initial velocity is 0. And let me just give you, so what if I throw? Well, if I throw something down, well, then this is false. Because now it'll have some speed. And this is what we mean here by velocity is 0. They're just dropping it versus throwing it down. Or, you could also throw it up. But our examples, because this is 0, it's always just being dropped. And you can see that right here in this picture. The little blue shirted dude is just dropping a ball. And interestingly, Here's a case where I was just talking about throwing the ball up. That would actually require this one. If we wanted to actually get the velocity there, so for this case, where this blue pajama wearing person is throwing the ball up, and that would mean, so we would have to use this full equation then, is what we'd have to do. And we'd have acceleration, which is 10, whatever time we want to put in. And then according to the picture, the initial velocity is 30. So I'm just looking at right here, it says v equals 30 at time equals 0. And so our equation gets adjusted to this. Instead of it just being 10t, we would have 10t plus 30. And then we'd get the velocity at whatever time you want to put in there. So let's just look at this over here to the right. It says 6 seconds, v is minus 30. Well, if we put 6 into this, we'd have 10 times 6, and we'd have our plus 30. Now, technically, and they didn't do this before, but when we use the full equation like this, we have to. G is technically down. The acceleration due to gravity points down, and we do need to give that a minus sign, which we're going to have to throw in over here. And then we get minus 60 plus 30, which is minus 30, which is then what they have. So just to be clear here, because I don't know if I'm going outside the book or not here, because their picture absolutely requires this equation, this picture that they have to the right. When we use this, whenever we use these equations, technically the acceleration in here should be minus g. And I'm just thinking here, I'm just going to scroll back really fast, just to connect back to something. Where was that? I think there was acceleration. Those ramps. Yeah, here are the ramps. So I wasn't sure they'd put the minus sign in because of right here they have A equals G. And that's where I wasn't quite sure if they were going to have them. It looked like they weren't. But now that I go to this next example here of this person throwing the ball up, well, now we absolutely 100% need the minus sign then. So the too long didn't read version is it really should be minus g. That's the TLDR. When you're dealing with gravity, it should really be negative acceleration because gravity's always pulling us down. And we define that as the negative direction. And then here's where they present the other equation. Again, these are the two. These are the two with a possibility of this, although I don't recall seeing this in the homework. But we do need this one for that person throwing the ball up. For the homework, I only recall seeing these, though. And you can see here's where they present the 1/2 AT squared. Now, again, they are using a positive G. Technically, meaning I'm going to get hardcore physics on you, that G should be negative. And again, when you travel down, let me draw a picture here. When your ball travels down, we tend to call this the origin system. You know, where you put your XY coordinate? Yeah, we're right there. And so when something falls down, we actually consider this a negative distance, like maybe minus 10 meters. This velocity, I'm just making up numbers here, just making them up. I'm focusing on the signs, though. So when something goes down, when it points down, well, that's a negative distance. We'd also call this a negative velocity because it has a velocity and its direction is down. And again, acceleration due to gravity is why it technically has a minus sign, because the acceleration due to gravity is also always down. So down, something going down, we consider negative. Something going up, we consider positive. Same to the right. Right is positive, left is negative. So technically, when you drop something, we would expect a negative distance because it's going down. And so technically, you should have the minus sign there as well. And here's giving another example. Another person dropping a ball, and now they're doing the distances. They want you to plug in, I think, some information here. Yep. And well, let's just take a quick look. Let's just look at this one right here where it says at time equals 2 seconds, we've gone 20 meters. Let's just take a look at that. I'm going to use this right here. Well, G is 10. At 2 seconds, I'm going to plug that in. That's squared. So it's always t squared there. So we got a half of 10, and t squared is 4. So 4 times 10 is 40. 40 divided by 2 is 20. We have our minus sign. We got minus 20. And now they are put positive 20 here. So, this is where the book isn't being technical enough, I would say, because they did give the distance equation without the minus sign. So our homework will be that way as well. The homework will also not use the minus sign. It is what it is. I want to tell you what the truth is of things, but without, having to overcomplicate anything. Let me just go back to this one. So at 2 seconds, we have 20 meters. Our distance is down. I mean, just to be clear, you can see the person's up here. The ball falls down, which we call negative. But they're just going to call 20. That's fine. But I want to look at the speed here for a second. They're showing the velocity as 20 meters per second. How did they get that? Well, they got that from this equation then. So again, these are the two important. What do you want written down right now? You want these equations here written down. And remember, when something's in free fall, A then is G, which is 10. And then, while technically should have a minus sign, our book isn't doing that. So we have this equation, V equals AT, where A is the acceleration of gravity. It should be technically minus 10. And we're doing it at 2 seconds. At 2 seconds, so I just plug in 2. So I'd have minus 10 times 2, which gives me minus 20. And you can see the speedometer they have here is 20. And if you do think about it, when you're driving your car, remember the speedometer gives you your speed. It doesn't tell you the direction. The minus sign here is a direction. It indicates going down in this case. But, your speedometer doesn't read that. Whether you're going up a hill or down a hill, your speedometer is going to read a positive 20. And let's just do this last one really fast. 6 seconds. Let's get the distance and the velocity at 6 seconds. And again, how do we do that? We use these two equations, except A is G. So we'll have G to get our distance, and we'll have GT to get our velocity here. And I'm just going to plug in the numbers. G is 10. I'm doing 6 seconds. We got to square that because it's 1/2 GT squared. And then here it's just GT. G is 10. Time is 6 seconds. And, well, this one's easy enough. 10 times 6, 60. So if I would draw my arrow here on the speedometer, I'm going to have it point towards 60. And then over here, I'm going to have to think a second because 10 divided by 2 is 5. And then 6 squared is 36. So that will be 180 then. And then that's the what we put in for the meters here. I had to say the speedometer here is actually pretty interesting because, the odometer part, the part that reads how far you travel, that doesn't have a minus sign either. That is your distance traveled. So your car doesn't keep record of the direction. In other words, your car doesn't have the vector part in your dashboard. Your dashboard just reads the number. Your dashboard it never gives you the direction unless you get a GPS system or something or a compass that's telling you you're going north and south and stuff like that. But your speedometer and odometer do not track the minus sign. Giving an example here of the acceleration due to gravity. So this actually happened, I'd say maybe 1970 when they went to the moon and an astronaut was on the moon. And you can find this video if you, I'm sure it's on YouTube for sure. He dropped a feather and he dropped a hammer and they fell and hit the ground exactly at the same time. And this was Galileo's big discovery, is because when you drop a feather, it seems to fall slower than the hammer does. And that ultimately has to do with air resistance. The discovery here was that gravity accelerates all objects the same. So on Earth, the feather still falls with gravity at 10, and the hammer also still falls with gravity 10 meters per second. That's the acceleration down. And now why the feather falls slower is because the air resistance has more of an effect on the feather than the hammer. That's because the hammer has a lot more mass, and it just can plow through all those air molecules, not be too bothered by it. Where the feather's very light, and now all the air molecules affect its fall, makes it fall a lot slower. So when we do drop a feather and a hammer, the feather falls slower because of air resistance. But if we take away air resistance, and that's what they're showing with this tube, they're trying to draw a vacuum tube. So a vacuum tube is where we take a vacuum pump, and we literally pump out all of the air in a way that keeps it sealed. And so the container then has nothing in it. It's just space. There's no atmosphere. Now, we can't get that perfect. We can't get every single molecule out, but we can get pretty close. And we certainly can get to a point where you won't see air resistance anymore. And that's what they're showing here. In a vacuum where there's no air resistance, then you will see a feather and a hammer drop with the same acceleration. And let me just say something here. When I was reading the book, and just thinking and preparing for things, this statement, I'd say, really bothers me. And that's because I try to present what's true, what you need to know, in this the most straightforward way to make it understandable. And stuff like this makes me feel like it's getting more confusing. And I just don't like how they say acceleration is how fast changes. Got it? It's just, why are you being tricky? Why are you being tricky there? Why don't you just say acceleration is your speed changing, your miles per hour. When you're at a stoplight, in order to go from 0 miles per hour to 50 miles per hour, you have to accelerate. That number we give acceleration is what causes velocity to change. So to me, it seems like they're just trying to be unnecessarily tricky. How fast changes. And it just seems unnecessary to be that tricky. Acceleration is it's your pedal on your car. It's called the accelerator. The accelerator gives you a change in your speed. If there was no, and this again, I think everybody can understand, if there was no accelerator in your car, well, then it's not going anywhere. You're not going to be able to change your speed if you don't have acceleration. And they're making a last comment here. Goes back to this equation. They are using A as, I just want to say, to be clear, A can be any number, any number. It's just that our book is focusing on gravity. And that's why you're seeing the G here all the time. So if you look to the right, you can see 1/2 gt squared. It's because they're focusing entirely on free fall. I just want to say that again. That's what they're focusing on, free fall. That's why you see just the G. But A can be any acceleration. So for instance, this applies to your car driving. If you accelerate at 2 miles per hour for 60 seconds, well, this will give you how far you traveled. So this applies to your car, to airplanes, applies to everything. We're just focusing on in free fall, though. And what the book is pointing out is you can also use this equation to solve for t. So if we multiply both sides by 2, that'll cancel out this half, and then get the 2 on the left. If we divide by g, so divide both sides by g, then we get this. So I divided both sides by g. Then finally, to get rid of the squared, we'd have to take the square root of both sides. And then this is where they get the book expression here, square root of 2d over g. And I just want to be clear, it's not like this is some new equation or anything. It's just this one rewritten. It's the same relationship. It's just written in a different way. And that's free fall. And velocity vectors. So what is new here to say? Because I've been trying to talk about not too much that I see. I do like this little picture here for a moment. I want to mention because there's something that I think is perhaps a little confusing about this picture. And the reason I say that is because they're always using A. You can see they're always using A for acceleration. They're always using a red arrow that looks the same length. And same with velocity. The velocity is always the same length. And I think there might be a little bit of confusion here. So I just want to say this, just my little bother with this picture is that your car, if your foot is on the pedal, then you have this forward acceleration because your foot's on the pedal, you're giving your car gas, you're accelerating forward, and because you're moving forward, your velocity is also that way. But when you get to, well, now you see there's a cliff. I guess that's what's happening in this picture. You now see a cliff. You're moving towards the cliff. So your velocity is still this way, but now you hit the brakes. And so the brakes is a different acceleration. It's not, remember, before you're hitting the accelerator, you're pushing it to the floor. Now you're switching your foot and you're hitting the brakes. The brakes causes a different acceleration, and that points to the left. And that arrow is not going to necessarily be the same length of the other arrow. In other words, there's no reason to think that these red arrows have to be all the same length. For certain, these lengths are going to be different. And then finally, so apparently, God, this is a gruesome picture, even though it's kind of cartoony. You didn't brake enough, and now you're in serious trouble. And now this acceleration, this is what I guess that bothers me the most, is this acceleration now is entirely gravity. It's no longer A. I mean, technically you can use A, but it's not these A's up here, though. And that's what bothers me. It makes it look like these accelerations are kind of all the same, where this first acceleration is your foot on the pedal. The second acceleration is your foot on the brake. And this third acceleration is free fall. This is from gravity. And I just want to distinguish what those accelerations were there. And that is the text. Give me a moment and I will switch to some homework. All right, so here is the practice homework. And I'm just checking out the first one. So at the top left, you can see 1 of 13 here. And just like last time, I don't want to do all of these because it's meant to be practice. I still want, some of these to come to you unseen. So I'll do every other here. Here's the first one. While you are in a bus that moves at that speed. So here we go. We have a speed. Notice they didn't give us a direction. Just say it's moving. So all they've given us is a speed. Kilometers per hour. You walk from the back to the front. Oh, okay. So let me actually get a different picture. So here's our bus, and it's going 100. And you walk from the back to the front at 10 kilometers per hour. And it wants to know, what is your speed relative to the road? So that's a person standing out here looking at this and observing what's happening. So they're seeing the bus go 100 to the right, and this person also doing another 10 to the right. And so you'll add these two together and you will see this person. When you look at this person, they will be passing you at 110 kilometers per hour then. And that's what they're going to want here, 110. Let me just say, if the person, so if we scratch all that, maybe there's a person on it, maybe there's a bird on the top, and the bird is walking this way, let's say at 2 kilometers per hour. Now if you look at the bird, well, you see the bus is going 100 to the right. 100 to the right. Remember, we define right positive. The bird's moving to the left. We define left as negative. And they're going left too. And so in that case, we'd see the bird going 98. So, but for our person inside, they want 110 there. All right, just a and cut edit there. But look, the truth is that I do go through the homework and answer all the stuff because, I think I know physics. So I do take the perspective like, hey, is the book right here? Or what is the book doing? So I know when I talk to you all. So I do go through and answer all these. Unfortunately, I can't reset that though. And that's what I was trying to do there to see if I could reset this assignment for me. And I can't because I'm not officially a student in the class. I can't reset this assignment for myself. So looks like I'm stuck with you always seeing the answers ahead of time. But we can still talk about them. I wish I could. I'll still look into that in the future to see if I can figure out how I can go through the assignment, confirm that I agree with these answers, and then see if I can clear it again so when I talk to you with again, the answers won't all be here. But here's number 3. What is your average speed in kilometers when you drive? So here they go. They're giving us a change in our distance. We're going 160 kilometers. That's our distance change. And our time change is 2 hours. And then our average speed is just our change divided by time. And so we'll get, what was that? 160 divided by 2, which gets us 80 kilometers an hour. And then you can see I checked 80 kilometers per hour there. So number 5, the difference between speed and velocity. So speed, Let me say this again. I know you can see the answer already, but let me say this again. If I just give you uh, a speed, then that is speed. But if I give you a speed and direction, that's what in physics we call a velocity then. And so the difference between speed and velocity is literally direction. And you can see that's what I clicked. So we got here, a car is increasing its velocity due east. So this is, so you can see they used velocity because they're giving us a direction, east, for 10 seconds. Then slows down for 2 seconds. So let's just draw this out. A car is increasing its velocity. So that means its velocity is due east and it's increasing. So this is like being at a stoplight. You start at 0, then your speed increases. How does it increase? Because you're pushing on your acceleration pedal. So when you go from a stoplight, your velocity, say you're traveling east. I actually drew this to the west. Now that I think about it, I suppose I need to do that correctly. So going to the east, if you're at a stoplight, there's your stoplight. You're going to travel. How do you travel from 0 to the speed limit? Well, you'd have to have an acceleration also going that direction. So the first acceleration is to the east. And then they're saying you slow down. So let's say you're at some point right here then. Your velocity, because you're still going east, means your velocity is still going east. But if you're slowing down, that means your acceleration is now going negative. It's turned the other way. Because that's how you get the velocity to slow down. If the velocity is going to slow down, then you have to have an acceleration going against it. And in this case, then it goes to the west. And then you can see I clicked east, then west. So just to say that again, how about this example? That you're at this stoplight, and here's another stoplight. When your car's here, you hit the accelerator pedal, and that gives you a velocity. And now say you're right here, and you see the light turns red. And you're like, oh, all right, well, I'm traveling towards the light, but I need to slow down. So I hit my brakes, and the brakes cause an acceleration that slows me down. Now, you might call that a deceleration or braking or a negative acceleration. All that is the same. All that's meaning the same thing here. But either way, when you start from a stoplight, your acceleration is in your direction. But when you're braking, the acceleration is against you because that's what slows you down. That's what changes your velocity. And that's where we go from east to west. That's how we go from east to west with our acceleration. And what is the speed acquired by an object in free fall? So free fall means our acceleration is only gravity. And they want to know the speed. So remember, there's 2 equations here. They gave us this one to use and this one to use, where A can technically be any acceleration, like your car, airplane, all that type of stuff. But since we're dealing with free fall, A is going to be G here. So if we want the speed, it's going to be GT, where G, acceleration due to gravity, is 10. They're saying it's in free fall for 4 seconds, and so our 10 times 4 is 40. And you can see then I clicked 40 meters per second. In this one, in its first second of free fall, so free fall again means A is G. These are our two equations we're using. A dropped softball has a distance, okay? So the last one asks for velocity. That's this one. This question is asking for distance. That's this one. So I'm going to use that equation, but with A as G. And G is, that's a sloppy 2. G is 10. And they're saying the time is, what did they say? 1 second in its first second. So that's 1 squared, which is 1. And then half of 10 is 5. And then you can see I clicked 5 meters. And the last one, we have a car takes 10 seconds to go from those two velocities at constant acceleration. So, well, that's interesting because that actually is using this full equation from Newton. Just to say this again, this is the full equation from Newton in calculus. For all the problems, though, this has been 0. For all the problems we've done so far, this has been 0, and so we just have that. And I just want to state that's still true. Notice our information. It says time is 10. It says time is 10. And I'm just going to use these parentheses to show where I'm going to fill in my numbers. So our time is 10. The acceleration is, or we're not in gravity, so we don't know the acceleration. We don't know the acceleration. But notice they're saying from v equals 0. This is the initial velocity, and they're saying it's 0. And then they're saying, so they're going from 0 to 24. 24 is the final velocity. And we actually have this same equation again, v equals at. But they mentioned v initial. So they did that right here by saying v equals 0. So they haven't done that before. And I'm just trying to show how that incorporates in. That would incorporate in by using Newton's actually full equation there. But it's still 0. So nothing in the long run changed. And then we have this piece of math. And if we divide by 10, we get then that our acceleration is 2.4. And I didn't check this one. So 2.4. And that's our answer. Well, there is the homework. If you have questions, make sure to email me. Talk to you in the next one.